Good. So then in the next half an hour, because I don't think we need more, and also we are a little bit late, we will now, after this motivation of REML, get started on where we actually apply it to and what the basic foundations of it actually are. And so the main thing that we are now dealing with can be framed as covariance component estimation. And as I said earlier, in principle, of course, you can also do a covariance component estimation using maximum likelihood. There's actually a very good book by Searle, which is called Variance Components, that explains the whole thing in a much more comprehensive way. Components. But in neuroimaging, covariance components estimation is always done using REML. Yeah? So one can do covariance component estimation using maximum likelihood or restricted maximum likelihood. Because we are doing neuroimaging, and we will focus on doing covariance component estimation with REML. Yeah? So then, of course, the first question is, what does this mean in terms of covariance? What are covariance components, and what is the model that we are dealing with? And that's in some sense similar to last week when we discussed generalized least squares. So the main point here again is that we are dealing with a GLM, so with our standard GLM as always. However, the errors are distributed now not in a spherical manner, but with some non-spherical covariance matrix parameter or covariance matrix V lambda. So remember last week we just had some V where we said V is not, sorry, not the estimate. V is not the spherical matrix, so it's not just a diagonal matrix with the variance parameter on the diagonal, but it's different. It's still positive definite, of course, because it's a covariance matrix, but we didn't specify anything more specific. And this week, and the way it's done in covariance component estimation in neuroimaging, we impose some more structure. So this V lambda means something which we will look at in a second. So this is of course the same thing as saying, like previously, that our data is distributed according to a multivariate normal distribution with expectation parameter x beta and covariance matrix V lambda. And just for completeness, everything else is of course as previously. We have n-dimensional data points, we have an n times p dimensional design matrix, and we have a p-dimensional beta parameter vector. And the question is now, what is V lambda? So V lambda is given by the sum of k covariance component parameters times covariance components basis matrices. That's how I call these things. Let me first write it down and then I tell you in detail what these are. So the important thing is, of course, now the covariance matrix parameter of the GLM that we're looking at. And of course, it needs to be positive definite, so it just needs to be a proper covariance matrix. It needs to be symmetric and positive definite, so that it can work as a covariance matrix parameter in the multivariate Gaussian. And the structure that is then imposed here and is always imposed in neuroimaging is this sum of scalar parameters lambda I times covariance matrix basis functions, or covariance basis matrices, I think that's how I call them. Covariance basis matrices, that's how I call them. So these are matrices, so each Qi is one matrix, and covariance component parameters. So what happens here is that we have covariance component parameters, these lambdas, lambda 1, lambda 2, up to lambda k, and we have covariance basis matrices Q1, Q2, and so on. For I being 1, lambda 1, and Q1, we are actually back to the case of a spherical setting. So the first covariance component basis matrix, or the covariance basis matrix Q1, is always the identity matrix. Now, so let's look at a first example for V lambda. So if we example 1, if we define k to be 1, and we define lambda 1 to be sigma square, then of course this formula V lambda says that we only have I from 1 to 1, lambda 1, Q1, and because Q1 is always the identity matrix, we just have sigma square IN. So our GLM, our spherical GLM, as we had it all the time, is just a special case of this more general GLM with this covariance component structure. And to give you the most important example also right now, because this is the one that is always estimated in and formulated in fMRI, we let k be 2. Yeah, so in fMRI it's not like there are 10 covariance components and basis matrices and component parameters, but there are 2. Yeah, instead of 1 in the spherical setting, there are 2. But this requires then this whole business of covariance component estimation. Here the matrix Q2, which we need to specify, because Q1 is always already specified in terms of the identity matrix, takes this form. So it's based on the product of a matrix set with itself, where the matrix set is defined as follows. I is larger than j, and 0 if I smaller than j. So basically this what this yields here, so this thing here is the negative part of the exponential function. So if you think about the exponential function, and we have 0 here, then we are talking about this bit here of the exponential function, which goes down the further away or the larger away I is from j, and it's 0 elsewhere. The question why this is of interest to fMRI, and also kind of an intuitive understanding of this, we will do once we talk about random processes and this AR1 white noise business. So this matrix that is behind this relates to this thing in the SPM or the fMRI model formulation AR1 white noise process. It's not trivial at all how this matrix, what this has to do with the autoregressive process. So we will take our time to discuss this after Christmas. So that's something, so where this matrix is coming from, this is something for 2020, not right now. But right now we have the second example here, which then is our lambda 1 times in plus lambda 2 Q2, and our Q2 matrix is formulated like this. So this is the SPM also FSL covariance matrix. Yeah. So the main point is here that it's not in fMRI, it's not just this, but there is an additional thing that induces actually the temporal error correlations that we discussed at the beginning of last week. So if you watch the video again, we discussed error correlations, and these error correlations are modeled using this matrix here. And how exactly this is done and why it comes down to this exponential decay, this we can only really understand if we know what stochastic processes are. And because we need stochastic processes for random fields, we will discuss this only after Christmas. But for the moment, the main point is that we are now not interested in GLMs only anymore where we have a spherical covariance matrix, but we are interested in this linear combination of covariance basis matrices with covariance component parameters. And one other thing that is very important that I haven't said yet, the QE are assumed to be known. Yeah. So for example, this matrix here that we use in fMRI, this is a fixed matrix that we know, but the lambda I, these are the parameters, and sometimes these are also only referred to as the covariance components. They are unknown. Yeah? So when talking about estimating the model, we are not only estimating now the beta parameter and the variance parameter, but we're estimating the beta parameter and all the lambda i's. And then we can, of course, summarize the lambda i's in a vector lambda 1 to lambda k. So these are also now free parameters of the GLM that we are interested in. Yeah. So this is the model formulation for covariance component estimation. Again, the most important thing is that we now have a sum of covariance components. The sum is given by a linear combination of these lambda things times the basis matrices. The basis matrices we know. In fMRI, there's only one basis matrix in addition to the identity matrix, namely this Q matrix that is formed by multiplying the Z matrix with itself, and the Z matrix being filled in using an exponential decay. We will look at that in detail in January, but that's it. Yeah. So the whole covariance component estimation business is really just about this thing here, and in addition to what we assumed last week, that it's non-spherical, it's now based on this linear combination here. So that's the question.
Yeah, why is it only one additional covariance matrix?
Yeah.
Because, I mean, it would be, for example, like get ready to breathe again, right? Like in the example last week.
Yeah. So you watched the video.
Yeah, and it's like, is it? But you can, I can imagine multiple sources. So that's
yeah. So the thing with the respiration last week. So one thing is so again, this is about modeling the error serial correlations. If you know sources of variations like breathing, then of course you can put them into the design matrix. So the question is now where you put variability in the data. Why? Do you put it and model it in the design matrix, or do you model it in the covariance matrix? And in general, the idea would be everything that you really know and can describe, you put into the design matrix. Everything that is left, where you have no precise knowledge about, but you think that this might induce deviations from independence in the errors, you put into the covariance matrix, and then this exponential decay here is kind of the very general model for error serial correlations. So two errors being correlated, and the further away they are in time, the less they are correlated. You can, and this is actually also happening, you can also impose more structure in the covariance component. So for example, if you apply this in some form of repeated measures, ANOVA, then you could put into error correlations that relate to participants. And of course you can also come up with more complex error correlation models that are not based on something deterministic that you measure, but somehow motivated by something. So I think basically trying to put everything that you know into the design matrix, and then allowing for some serial correlation that I mean, what you could think of course, different forms of decay, so that you have a fast decay and a slow decay, things like that. Right now, actually, it's always a fixed decay of the serial correlations over time that is put in. So one could do more, but things like breathing, so deterministic things that you measure, you would rather put into the design matrix. Yeah. Good. Any other questions about this? Good. So then to summarize this, we can very quickly, you can of course just write the covariance component GLM as P beta lambda over the data is a multivariate normal with X beta and V lambda. The V lambda is lambda E Q E. Yeah, so that's if you don't go into details about it, you can briefly formulate it like this. And now if K of course is larger than 1, so if we are not only dealing with, maybe this, we should still specify that Q1 is always the identity. If we have K being 2, then we have one more parameter to estimate. And lambda 1 also always needs to be larger than 0. So that's the only additional complexity we put in this covariance component estimation business. So it's not really that getting that more complicated. And we could now actually estimate these parameters lambda I. So of course we still need to estimate parameters. And before we needed to estimate beta and sigma square. And now we need to estimate beta and lambda 1 to k, where in fMRI this then corresponds to, for fMRI, this corresponds to beta lambda 1, which is still the variance of the errors, because it relates to the identity matrix and lambda 2. Now, so we just have one parameter more. That's the whole thing. We could do this using maximum likelihood. And in the Searle book, you can read all about how this works for maximum likelihood. However, as I said many times now, in neuroimaging, this is done using REML. So read the Searle book, it's really a nice book. But we are looking at it when we are looking at neuroimaging. So we are now doing model estimation using REML. So model estimation under REML. The basic idea of REML is to estimate the error covariance parameters after remove or in a GLM where the X beta, so the deterministic effect, or in the literature you always also see this as being referred to as the fixed effect, but this is our deterministic expectation having been removed. And this is in some way similar also to what we did last week in generalized least squares. So do you also watch that video? Do you remember what the basic idea of generalized least squares was? To get to the generalized least squares estimator?
We are trying to find the best fit. We are trying to find the best fit.
No, that's ordinary least squares, and but I'm referring to generalized least squares that we discussed in the second hour last week.
I need to watch it again.
So the basic idea of generalized least squares was to make the error terms that were correlated to make them uncorrelated. So we used a matrix multiplication to basically get, sorry, I think it was like, to get to to get to a spherical GLM. Yeah, so the idea was we multiply the entire GLM equation by a matrix such that the errors become uncorrelated, and then we use the standard beta estimator in this transformed GLM, and then we back transform to the correlated case. So basically the whole thing was based on multiplying the GLM, doing the estimation in the transformed GLM, because there the standard beta estimator applies, and then looking how the standard beta estimator looks in the untransformed case. And the logic here for REML is somewhat the same. So again, we use a matrix multiplication to get to a form of a GLM that is different. We estimate the parameters in this different form, and then we return to the form that we actually use. So it's again this transformation of a GLM, estimating there, and then back transforming the estimates. The fundamental idea here is, I need to watch time a little bit. The fundamental idea here is to multiply the GLM with a matrix K, with a matrix K and which is n times r dimensional, such that kt times x is the 0 r times p matrix. Yeah. So we assume that this is somewhat like last week. We assume that we can find a matrix K that, when we multiply it with the design matrix, yields the 0 matrix. How we find this matrix K, we don't discuss now, because it will turn out in the very end, when we discuss the Fisher scoring algorithm, that we actually don't need to specify this matrix K. So the estimators that we will come up with for the lambda parameters, they will not depend on the matrix K. So this K matrix in REML is just an imaginary matrix, if you want, that motivates the whole thing, but it turns out that the precise form of K does not enter the estimates, so we don't actually need to specify it. It's a little bit different to generalized least squares, where we got this matrix that we need to multiply everything with from the square root of the covariance matrix. So there we have this thing that we need a matrix K like this, but this is in the GLS setting, and there we actually need this matrix K in the end when we want to compute estimates. Here we this matrix K, which is a different matrix, of course, because it's satisfying a different constraint, we never really need, but we need it to develop the theory, which is a little bit something to get used to, but that's nevertheless how it is. So the fundamental idea is that there is this matrix K, which we multiply with the design matrix to get a 0 matrix. This matrix K is also called error contrast matrix. Don't think much about this term because it will just don't think too much about this term. It's just how it's often referred to. The point is that if it's multiplied with the design matrix, it yields the 0 matrix. Now, let's have a look. So our GLM looks like this. And now we multiply the whole GLM with KT, like we did that last week, and we have a look at what happens. So if we now apply this transformation, of course we cannot really say something about KTY, but we can say something about this thing here, because KTX is 0, so KTX will be KTX beta will be 0 r times p times beta, which is p times 1. So oh, there's actually a typo in the script. This will be the 0 vector here. And our epsilon is still 0 n p lambda. Yeah. So the important point here is that we get rid, because we define the matrix K such that if it's multiplied with the design matrix, we get the 0 matrix in this transformed GLM. So this is here the transformed GLM. There are no beta parameters. Yeah, so we removed, this is what they always call remove the fixed effects. We remove the deterministic aspect of the GLM. Yeah, so we now deal with the GLM in which there are no beta parameters. There's just the errors. Yeah. And if we actually apply this here, so the transformation of the errors, then we can of course rewrite our GLM in terms of a PDF over KTY, because this will be KTY 0 R KT epsilon K. So this is again our linear transformation theory for Gaussians, which we also used last week, and we used when we talked about the beta parameter estimator distributions, and which you also have studied for the exam on the 20th, because it's part of the Gaussian preliminaries. So that's that. Oops, sorry, not the epsilon there, sorry, the V lambda. So this is, yeah, essentially this is just transforming the errors, which were distributed according to this multivariate Gaussian, and because they are multiplied by a matrix KT, they end up for the distribution of KTY in the covariance setting. And I think this is where I want to stop today, because the problem of restricted maximum likelihood estimation is then actually to do maximum likelihood estimation of lambda maximum likelihood estimation in this transformed model. Yeah, so we don't have to estimate any beta parameters in this transformed model because there are none, but we can estimate the lambda parameters. And then the idea will be, once we have estimated the lambda parameters, then we have an estimate of our V matrix, which we can use in the general least squares estimator to also estimate our oops, that's a little bit too much, to estimate the beta parameters. Yeah, so if you're wondering what happens with the estimation of the beta parameters, we will get to it. It was a little bit weird here. What's going on? XT. Let's forget about this. I'm not quite clear on this right now. We will do maximum likelihood estimation of the lambda parameters in a numerical setting in this thing. This is restricted maximum likelihood estimation. And once we have our lambda hat, we can use the generalized least squares estimator to also estimate the beta parameters in the original GLM. And then we have everything. And so next week we will start with this likelihood function for lambda, and look how this can be estimated. And this actually needs numerical estimation, so we will use a Fisher scoring algorithm, which is a variant of Newton-Raphson, of a multivariate Raphson thing, and this is what we will discuss next week. Yeah. So again, the fundamental idea of REML estimation is to transform the GLM that we are interested in. The GLM that we are interested in is now the GLM with these covariance components, so with this thing. And then we estimate in this transformed GLM. Once we have estimated there, we use our results to go back to the untransformed one. Yeah? Good. Questions for now? Good. Then let's stop here and continue next week.